altermagnetism. So altermagnetism is like a different kind of large field, such as a ferromagnet, antiferromagnet. So I believe this talk will be so attractive for you all. So, and the first speak is the title is Spintronics on Altermagnetism. Also, Shutaro Karube, please start if you're ready.
Thanks for the introduction, Chairman. So just a moment.
So can you turn on the video?
So
okay.
So could you allow me to show me on the video?
Okay, I will ask you. Sorry.
There is a restriction now.
Okay. Sorry.
Yes.
Maybe I'm asking. Okay, thank you so much.
Thank you very much. So.
Okay, please, sir.
Okay, so my name is Shutaro Karube from Kyoto University. So I'm truly honored to be invited to this fascinating international conference. And I would like to extend my gratitude to the committee members, like Yusi-san, and all the participants. Today, I have the privilege of presenting my research finding related to the altermagnetism. The topic that has been gaining the significant attention recently, and its connection to the Spintronics. So I will introduce the outline of the presentation. First, I will provide an overview of the background in the field of the Spintronics research, with a particular focus on using the spin current. Next, I will show you the history of the magnetism, especially highlighting the parity and the time reversal symmetries to discover the new phenomena. Next, I will introduce the emerging field called as altermagnetism and present the various intriguing phenomena within it. Furthermore, I will demonstrate how this magnetism can be utilized to generate spin current, leading to the potential application in Spintronics. Finally, I will conclude the presentation. So, as the background, we know the recent rapid development of the highly digitized society has led to the increasing the social demand for the low power consumption and the carbon neutrality. Therefore, there is a growing desire for high efficiency information processing technologies. In this context, the Spintronics is believed to offer the promising solution, particularly through the development of the magnetic random access memory. We know the MRAM. The MRAM is expected to address these challenges due to its non-volatile nature, the high speed operation, and the high information densities. It is estimated the market value of the MRAM will reach $30 billion by 2030, making it a crucial component in information carriers and processing devices. In fact, major semiconductor companies such as Intel, Samsung, and TSMC have entered mass production, and the MRAM is being applied in the products such as the smartwatches and the microcontroller units, MCUs. So, based on this background, what can Spintronics contribute to enhancing the performance of the MRAM? So the MRAM operates based on the reversal of the magnetization within the magnetic materials, which allows for the data rewriting. Traditionally, the common approach for achieving the magnetization reversal has been to use external magnetic field. Around the decade ago, the Professor Liu at MIT proposed an innovative idea to efficiently achieve magnetization reversal using the spin current. The spin currents consist of the flow of the electron spin angular momentum, which means they can impart a finite torque on the magnetization. So we can generate this spin current easily through the spin Hall effect that we know. There are two types of the MRAM. The one is STT-MRAM, which operates based on the spin transfer torque, induced by injecting the spin polarized current. Another one is just a SOT-MRAM, which operates using the spin orbit torque induced by the spin current via the spin Hall effect. Below, I provide the benchmark comparison between the existing SRAM and STT-MRAM and SOT-MRAM devices. Compared to the SRAM and the STT-MRAM, the SOT-MRAM offers significant advantage, including the non-volatility, the cell size, the lighting energy, and the durability. In particular, the SOT-MRAM, which utilize the spin currents, that demonstrate the superior characteristics in these aspects. Therefore, the spin currents play a crucial role in enhancing the MRAM efficiency compared to the existing conventional devices. However, there have been the challenges with the spin currents induced magnetization switching. So this method typically involves heterostructures composed of the ferromagnetic and the heavy metal layers, commonly used for the magnetization reversal, as shown here. In the case of the spin Hall effect, the generated spin current is perpendicular to the direction of the applied current. Therefore, to reverse the perpendicular magnetization, and the external magnetic field is required. So this field is necessary to break the symmetry of the magnetization reversal, enabling the deterministic switching. As a result, there has been the dilemma because the external magnetic field is still required for the magnetization reversal, despite using the spin current. Hence, there is a strong desire for entirely the new principles of the spin current generation that do not rely on the external magnetic field. Up until now, the generation of the spin current has primarily focused on the non-magnetic material, such as heavy metal. To explore the new principle of the spin current generation, it's worth considering the magnetic materials. Therefore, let's begin by briefly discussing the history of the magnetic materials. The magnetite, a substance we are familiar with today, has been known since ancient times, dating back to before the Common Era. The philosophers like the Thales also made references to magnets. Approximately 2,000 years later, the renowned scientist William Gilbert discovered the Earth itself to behave like a magnet. These magnets, they're now commonly known as ferromagnetic materials, that have neighboring magnetic moments aligned parallel to each other due to the exchange interaction. The overall magnetization, which is the volume average of the magnetic moments, the summation, can respond to the various external fields, such as external magnetic field, electric field, the spin currents, and more. This property makes the ferromagnetic materials versatile as carrier of the information. In practice, practically the ferromagnetic material find application in the wide range of the products, including the voltage, hard disk drive, HDD, and MRAM, and more. So it would not be an exaggeration to say the ferromagnetic material have been integral to human history, playing the significant role in the technological advancements and the various aspects of our lives. On the other hand, antiferromagnetic materials exhibits exchange interaction where the neighboring magnetic moments align in an anti-parallel manner. As a result, the net magnetization is zero, and they have intriguing properties such as the absence of the stray magnetic field and high internal exchange field, leading to the ultra-fast dynamics. However, this property can also be a drawback, as they exhibit a significantly small response to external fields. An example of this is the magnetic field response of the antiferromagnetic chromium oxide, where it is evident that there is no net magnetization. So Ruinel, who laid the framework for the antiferromagnetic theory through the molecular field theory, remarked in his Nobel Prize lecture that while it is theoretically interesting, it is unsuitable for the practical application. Therefore, it is crucial to find a way to harness the advantages of the antiferromagnetic material while making them suitable for the practical application. To maintain the characteristics of the antiferromagnetic coupling, while making the material exhibits the ferromagnetic-like properties, it's essential to consider the symmetry arguments, particularly regarding the parity and time reversal symmetry. The electric field and the magnetic field play significant role in the breaking of these symmetries. As is well known, the electric field break parity reversal symmetry, and the magnetic fields break time reversal symmetry we know. So this understanding can be easily grasped through the analogies such as the considering heterostructures of the dissimilar materials, of the thinking about Ampere's law. The example of these effects are observed in various material systems, as shown here. Particularly ferromagnetic materials possess the spontaneous magnetization, the breaking time reverse symmetry, and exhibiting the intriguing property. Therefore, if it were possible to break the symmetry of the antiferromagnetic material, in a way that mimics the ferromagnetic behavior, while preserving their unique characteristics, it could potentially lead to the properties akin to the spin splitting, similar to those found in the ferromagnetic material. So from the perspective of the breaking time reversal symmetry in the antiferromagnetic material, the concept of the altermagnetism emerged, which will be the focus of this presentation. Let's briefly explain this novel magnetic phenomenon. First, let's consider the typical antiferromagnetic material for the comparison. The nickel oxide is a well-known antiferromagnet with a rock-salt crystal structure, as shown here. The rock-salt has a high crystal symmetry, preserving both the parity and time reversal symmetry. Consequently, there is a spin degeneracy in the electronic band structure, making it unsuitable for the practical applications. However, even within the category of the antiferromagnetic material, some have a lower crystal symmetry, This is where altermagnets come into play with a ruthenium dioxide having a Luchil structure as a prototype. The intriguing crystal field anisotropy exhibited by these materials breaks both parity and time reversal symmetry. As a result, it was predicted the altermagnet could host the split electronic band structure. This makes them akin to momentum-dependent ferromagnetic material, offering the potential application and the unique properties. At the first glance, altermagnetism might appear to be a theoretical concept, but it has indeed been experimentally observed. So researchers have detected spin split band structure in materials exhibiting altermagnetism. These observations were made using the X-ray magnetic circular dichroism and the photoemission electron microscopy. We know the XMCD PIM. In this technique, the circularly polarized soft X-ray are used to irradiate the ruthenium dioxide, in this case 110 plane, and the secondary electron ejected due to the photoelectric effect are measured. The authors confirmed the band structure obtained through the first principle calculation matched the one obtained from the PIM measurement. So what makes this observation particularly intriguing is that it's employed XMCD, which is typically used for the ferromagnetic materials rather than XMLD, the commonly used for the antiferromagnetic materials. So this highlights the key points. Altermagnetism involves momentum-dependent ferromagnetic aspect, which was successfully observed. Therefore, it is clear that altermagnetism is not just a theoretical concept, but a real phenomenon that has been experimentally verified. In addition to the prototype material ruthenium dioxide, there are the various other candidates for the altermagnet. The one intriguing candidate is chromium antimonide, which, like ruthenium dioxide, has a crystal field surrounding the magnetic element chromium. It is anisotropically coordinated with respect to up and down moment. The chromium antimonide exhibits the higher spin splitting energy and low temperature than the ruthenium dioxide, making it even more promising for the practical application. Furthermore, the altermagnetism has been predicted in a range of the oxide and the compound, indicating the emergence of a new field of the magnetism. This ongoing exploration of the altermagnetism in the diverse materials holds great potential for advancing our understanding of the magnetic phenomena and expanding the possibility for the innovative application in the magnetism related to technology. The film surface arises from the altermagnetism, exhibits an analogy similar to the phase symmetry found in the superconductivity. It is well known the phase of an S-wave superconductor that is described by the BCS theory is isotropic. On the other hand, the ferromagnetic material exhibits the Zeeman splitting, also possess S-wave-like film surface, as shown here. Unconventional superconductors like a cuprate, high TC, the superconductors are known to have an isotropic phase, such as a D-wave symmetry. The altermagnetism features film surface with a similar characteristics too. So this classification suggests the altermagnetism may indeed be an important and previously hidden facet of the magnetism. The analogy between the film surface of the altermagnetism and the phase symmetry in the unconventional superconductor provide further insight into the unique and the intriguing nature of the altermagnetic material. The altermagnetism that has been predicted to exhibit various symmetry beyond the D wave, including Z and I symmetries. The emergence of G's spin symmetry is closely linked to the crystal field symmetries. Through the classification based on the Laue group, it becomes possible to organize and understand these the different spin symmetry in the altermagnetism. This systematic approach to categorizing the spin symmetries in altermagnetic material that helps provide a comprehensive understanding of their unique magnetic property and the behaviors. We now would like to compare with the ferromagnetic, the antiferromagnetic, and discuss the altermagnetic families. The altermagnetism, with its ability to acquire the anisotropic spin density due to the crystal field's anisotropy, enables momentum-dependent spin splitting. The origin of the term alternate lies in the fact the crystal field anisotropy provides a different band for up and down magnetic moment, leading to this unique property. The altermagnets combine the advantage of the demagnetization, the various spin symmetries, and the significant spin splitting, which are characteristics of both ferromagnetic and antiferromagnetic materials. This makes them the promising candidate for the Spintronics application. The anomalous Hall effect is an intriguing phenomenon in the normally ferromagnetic material, and it has also been observed in the altermagnet due to their low crystal symmetry. In 2020, the existence of the anomalous Hall effect was predicted in ruthenium dioxide, and the finite Berry curvature was indeed demonstrated through the first principles calculation. 2 years later, in 2022, the anomalous Hall effect in the ruthenium dioxide was experimentally observed. The data shows a nonlinear behavior characteristic of the anomalous Hall effect with the conventional Hall effect component already subtracted. The table shows a comparison of the anomalous Hall conductivity between conventional ferromagnetic material, the non-collinear antiferromagnetic material, and the altermagnet. And in this case, ruthenium dioxide. Although applying the significant magnetic field of the 50 Tesla, as shown here, experimental value exceeding the 1000 the Siemens over the centimeter that have been reported, surpassing the values seen in the ferromagnetic material. This remarkable anomalous Hall conductivity in altermagnets opens up a new possibility for application in spintronics and suggests the altermagnets may offer unique advantages in terms of the spin transport and the manipulation. It's fascinating to hear about the potential for the observing the phenomena that typically associated with the ferromagnetic material in altermagnets, and the possibility of achieving the tunneling magnet resistance TMR in the altermagnetic system. While these phenomena were initially theoretically the prediction, the fact the theoretical work related to the TMR in the altermagnet has been reported by different groups in 2022 that suggests a high likelihood of the experimental realization. Of particular significance is the prediction of the TMR ratio, reaching up to the 500%, which is close to the values observed in the ferromagnetic materials like iron MgO tunnel barrier. So we now are actively preparing an experimental setup using the altermagnet altermagnets, the prototype ruthenium dioxide with titanium dioxide, as shown here. The addressing the challenge of the controlling the Nel vector reversal in the free layer is a crucial aspect of this research. The researching the TMR in the altermagnet hold greater potential for the advancing our understanding of these materials and their application in spintronics. The altermagnetism holds the potential to overcome the challenges associated with the spin current induced magnetization reversal, as it has been theoretically predicted to enable the generation of the spin currents by leveraging the characteristics of the giant splitting. This phenomenon is known as the spin splitter effect recently. So this effect is distinct from the spin Hall effect mediated by the spin-orbit interaction in heavy metal. This distinction arises because the spin polarization direction of the generated spin currents depends on the Nel vector, making it unique. So what material has altermagnetism and the electroconductivity to generate unconventional spin current? So this is just a ruthenium dioxide, as I mentioned before. So this oxide is indeed the versatile material that plays the significant role in exploring and the validating the phenomena related to the altermagnetism. Here's the brief overview of the ruthenium dioxide. This oxide has a Ruchil type crystal structure and really low resistivity like metals. The Nel vector is aligned to the 001 direction, the C-axis. Surprisingly, the oxide was found to be an antiferromagnet at room temperature by means of the neutron scattering recently, 2019. Given its unique combination of the metallic behavior, the magnetic order, and its physical property, such as Dirac nodal line, the superconductivity, and the intrinsic anomalous Hall effect, as I mentioned, this oxide holds significant promise for the advancing the research in spintronics and related fields. Its role as a prototypical altermagnetic material provides a valuable insight into the potential application of the altermagnetism. For the oxide, so we employ the RF magnetism sputtering. So this sputtering they enable us to prepare the epitaxial ruthenium dioxide onto the single crystal substrate like a sapphire or the MgO. So based on the this condition, so these conditions ensure the growth of the high-quality ruthenium dioxide thin films on the chosen substrate. So moreover, to study the anisotropy of the spin current generation based on the relative orientation of the Nel vector and the applied current direction. The various crystal planes of the ruthenium dioxide, such as 100, the 101, the 001, have been prepared. The result from the ruthenium dioxide 101 is shown in the XRD and the TEM and the XPS, and the other analysis demonstrates the high crystal quality of the prepared epitaxial thin film. The high quality crystal preparation is essential for the studying the intrinsic property and the anisotropy associated with altermagnetism induced the spin current generation. So here I'd like to show you the experimental result regarding the spin current generation from the ruthenium dioxide. We conducted an experiment to detect the spin currents generated in the epitaxial ruthenium dioxide film, and then measure them using well-established technique like SDF-MR. The process that involves depositing continuously perma layer in situ onto the ruthenium dioxide film, creating a microstructure through the lift-off process, and designing the waveguide type devices. The SDF-MR method utilizes an AMR effect in permalloy, which rectifies the resonance signal, resulting in the observation of the DC voltage. By measuring the effective magnetic field induced in the permalloy layer by the spin current, we can evaluate the spin current from the material. This is the raw data obtained from the bilayer structure and how the resonance spectra are separated into the symmetric and asymmetric voltage. The observation, the signal's intensities differs between positive and the negative resonances that indicates the presence of the signals resulting from the Smith-splitter effect. By investigating the in-plane angular dependence of the external magnetic field, we can identify the direction of the spin polarization X, Y, or Z. The angular dependence of the symmetric and asymmetric voltage helps determine the spin polarization component, revealing the presence of the Z and the X polarized component, in addition to the spin Hall effect with the Y polarization. These results suggest that the spin current generated in the ruthenium dioxide have a contribution from the multiple spin polarization directions, providing a valuable insight into the underlying physics of the altermagnetism in the induced spin current generation. We further conducted additional experiments involving the insertion of a copper layer, and of course, they obtained a similar result like previous case. The observation of the unconventional Z and the X component in the measurements indicates the spin current generation is indeed as a result of the Smith-splitter effect. Here I emphasize again. So these results helps to reinforce the conclusion. The spin currents generated in ruthenium dioxide exhibits unique spin polarization components, which are not solely due to the exchange bias effect. So this further strengthens the evidence for the altermagnetism induced the spin current generation in the ruthenium dioxide-based system. So these results on the ruthenium dioxide 100, 101, 001 samples, along with varying the current direction with respect to the specific crystal direction angle phi c, have yielded variable insights into the spin polarization component X, Y, and Z of the generated spin current. It is intriguing to note the finite values are observed for the Y component in all cases. So just a moment. Oh. Sorry, my presentation doesn't work well now, so just a moment.
Okay. Now we can see the slide page 23.
Oh, really? Oh, that's fine.
Yeah.
Thank you very much. Okay, yeah. Now I can continue. Thank you very much for your help. So yeah, let's go back to the results. So these results are on the ruthenium dioxide 100, 101, and the 001 samples, along with varying the current direction with respect to a specific crystal direction phi c. They have yielded our variable insight into the spin polarization component. It is intriguing to note the finite value observed for the Y component in all cases as shown here. Furthermore, the ruthenium dioxide 101, as shown in red color, exhibits anisotropic behavior in response to the change in the angle phi c, which is a significant finding. Additionally, when examining the X and the G components, it becomes evident the ruthenium dioxide 101 that displays both finite and anisotropic behavior. These results indicate the presence of both the offset, the spin Hall effect, and the spin splitter effect. Surprisingly, the magnitude of the spin splitter effect is comparable to that of the spin Hall effect. So this is a substantial discovery that contribute to a better understanding of the spin current generation in ruthenium dioxide-based system. So the discussion regarding the crystal orientation, the crystal plane, is quite enlightening. It appears the spin splitter effect could not be observed on the ruthenium dioxide plane other than the 101. So regarding the 100, the obtained thin film has been found to have a high resistivity, leading to a higher scattering rate gamma. Since spin splitter effect is an intrinsic phenomenon, it becomes difficult to generate a spin current when gamma is high, based on this formula of the TOD spin conductivity. Therefore, it can be inferred the effect could not be observed on this plane due to the elevated scattering rate. Moving on to the 001, where the resistivity is considerably lower, like a 101 case, the explanation based on the gamma alone is not sufficient. The exact reason for this observation remain unclear, unfortunately, but it is currently believed the 001 direction does not allow for the spin current generation due to the spin symmetry consideration. These insights provide a variable context for understanding the spin splitter effect's dependence on the crystal orientation and the scattering rate in the ruthenium dioxide-based system. The comparison between the spin splitter effect and the spin Hall effect provides the variable inside their differences. Both are the intrinsic phenomena, but their origin are distinct. The spin splitter effect is related to the altermagnetism, while the spin Hall effect, we know that it arises from the spin orbit interaction. A crucial distinction lies in the orientation of the spin polarization of the generated spin current, concerning the direction of the the charge current. In the case of the spin splitter effect, the spin polarization, the direction depends on the Néel vector and is not constrained by the current direction. This characteristics allows the spin splitter effect to overcome the challenges associated with spin current induced magnetization switching, as discussed earlier. In summary, the spin splitter effect and the spin Hall effect offer the different mechanism for the generating spin current, with the former providing certain advantage in terms of the spin polarization direction, and addressing the specific challenges in the Spintronics application. I'd like to show you the demonstration of the field-free switching experiments with ruthenium dioxide 101. By applying the charge current into the 010 direction, we can generate the depolarized component of the spin current, allowing us to achieve the field-free switching with clear hysteresis behavior, as shown here. The presence of the multiple magnetic domain in cobalt due to the exchange bias from the ruthenium dioxide has led to the memorist behavior in response to the varying current amplitudes, interestingly. In addition, the whole loop shift measurements have shown the effective magnetic field in the z direction linearly changes with the applied current, providing the further evidence for the origin of the spin splitter effect. By leveraging the ruthenium dioxide altermagnetism, we have successfully demonstrated the application of the Spintronics in our research. This achievement showcases the potential of the altermagnetism for the spintronic application and paves the way for the further development in the field. The challenges of achieving the higher conversion efficiency from charge current to the spin current in our research is indeed significant. The theoretical prediction of the 30% efficiency contrasts with the experimental observation of around 1% efficiency, which presents a notable disparity between the theory and the experiment. So this issue has been reported by various research groups, underscoring its importance. To enhance this conversion efficiency, the further research into the magnetic domains within the ruthenium dioxide is essential, we think. As observed in a material like the hematite, antiferromagnetic materials also exhibits the domains, and these domains may hinder the spin current generation in the ruthenium dioxide case. In investigation of the domain size and the domain reduction, the strategies will be crucial for the improving the conversion efficiency in the future. So finally, I'd like to summarize my talk, especially regarding our result. First, epitaxial ruthenium dioxide as an altermagnet has been successfully prepared by means of the magnetron spotting. The next, unconventional spin currents have been generated via the spin splitter effect driven by the altermagnetism. Finally, the field-free switching in an adjacent ferromagnetic layer has been demonstrated using the G-polarized spin current via the spin splitter effect. So if we are interested in this topic, please refer to our paper as shown here. That's all. Thank you for your attention.
Thank you, Professor Shutaro Karube. Excellent talk. So let's move on to the question session. And it has 7 minutes, so you can ask any question if you have. Okay. Francesco, please. I'm asking.
Yes, you hear me? You hear me?
Yeah.
Yes.
Yeah.
Okay.
Thank you for the interesting talk. It's really an exciting topic. I already seen some other talks about it, and I'm full of questions and interest. So you showed a temperature dependence of the curves, and it seemed that the effect is a lot bigger at low temperature. Can you elaborate a little bit on the temperature dependence on this effect? Is intrinsically higher at low temperature, or we can find also material that then eventually could bring it at room temperature?
So you are talking about the spin splitter effect or
the spin splitter? No, the anomalous. Both anomalous effect and spin splitter effect.
Okay, I got it. So that's an important point. Actually, this phenomena is originated from the intrinsic one. So the temperature is one of the most important factor to enlarge the efficiency. So as you mentioned, that if we decrease the temperature, we can expect high efficiency of the spin conversion in the ruthenium dioxide. Actually, there is a report regarding the topic from the Ralph group in Cornell. So the comparison with room temperature at 10 Kelvin, they got higher efficiency, surprisingly. So the temperature is very important in this phenomenon.
Okay, I will unmute you, Francesco. Okay.
Yeah, sorry, I muted myself. Yeah, thank you for the reply. So, but you still hope that we can reach room temperature value that are high enough to make it useful for application, right? It's
Yes.
not like it's not impossible. It's not like physically very difficult.
So at room temperature, so as I mentioned in this slide, we have to reduce the magnetic domain, the ruthenium dioxide, because there is a cancellation out of the efficiency due to the magnetic domain. So first of all, we have to check the size of the domain, somehow using the method. The next, based on the size, we have to investigate the spin current generation with the variable the sample width device. So then we can conclude whether the domain is crucial on the spin conversion or not. Yeah.
Okay. Thank you very much.
Thank you.
Okay. Next, Dr. Fang, please ask.
Hi, Dr. Karube. Thanks so much for your talk. This is Fan from Stanford. I have two questions here. One is, if you go back to page 22, I remember you mentioned about exchange bias in the end of the, exchange bias are not necessary in the torque. So can you say more about that? Why the exchange bias is not that important for the ruthenium oxide to generate spin polarization?
So in this slide, I wanted to distinguish the effect. So the exchange bias is not essential for the spin current generation, depending on the Néel vector here. So in the previous slide, as I mentioned, this is just ferromagnetic and antiferromagnetic bilayer. So in this case, we should carefully consider the exchange bias effect on the spin current generation. So we got the specific feature. We found the unconventional Z and X polarized spin current. So therefore, we have to ensure the exchange bias is not essential for this spin current generation. Therefore, I further conducted the experiments with the copper insertion, breaking the exchange bias between the permalloy and the ruthenium dioxide.
But if there is exchange bias, after you got deposited the ruthenium oxide, would that help with a bigger spin polarity, unconventional spin polarity?
Yeah, actually, yeah. We already checked the amplitude of the exchange bias in case of the permalloy ruthenium dioxide bilayer. But then we found a quite small exchange bias in the samples. So now, as I mentioned, we performed the FMR phenomenon to extract the spin current generation. So, for example, the resonance is happened at 150 millitesla, as shown here. So, this resonance field is quite larger than the exchange bias. So, we can neglect the effect on the spin current generation.
Thank you.
In this case, the exchange bias is also important to other applications. Yeah, I agree with it.
Yeah. another quick question is in
Okay,
the last
sorry.
Oh.
That's almost time to move on to the next speakers. So, please discuss in the
Yes,
for
yes, of
example,
course.
yeah,
So
yeah.
could you send me the email, the Dr. Fenshu?
Yeah, thank you.
Or you
Yes, thank you very much.
or you can discuss in the gather town.
Yes,
want.
yes,
Yeah,
of course,
it's
of course.
actually, yeah.
Thank you very much.
Okay. So thank you, Dr. Karube, for exciting.